Hello, welcome back to the channel. We continue to review the Understanding Construction Drawings textbook. This video is about Unit 36, and that is Seismic Considerations. This is critically important in some locations. For example, in the US, the state of California has the California supplemental exam after the architectural exam, so that the architects know how to design and plan for the seismic conditions. So after this unit, we will be able to identify the seismic design category, then explain how earthquakes affect the buildings, and find information about seismic considerations on construction drawings. So let's begin with the basics. Um, we need to understand where the earthquakes occur. So in some areas, earthquakes are a potential hazards, and buildings in those areas must resist the seismic forces. So earthquakes are one of the three types of loads that buildings must support by providing load paths through the structure and back down to the ground. So we know that all the building have dead loads, and that's the weight of the building materials. Then the live loads, and that is something that can change or move around the building, such as, for example, people and furniture. And then there are dynamic loads, and those are the loads that produce varying amounts of force, and that is snow, wind, or earthquakes, and those are the seismic loads. So many of the methods used to resist earthquake damage will also prevent damage from strong winds. And the seismic design category map actually is represented here in our unit. So I highly recommend to go back to the textbook and review those maps, because they show the seismic design standards for all areas of the United States. So please just check them out and see how that is located and where that is located. And there are a few seismic design category risks. So SDC, or seismic design category, has a few variations. So let's take a look at them. A is very small seismic vulnerability. Then B, low to moderate seismic vulnerability. C is moderate seismic vulnerability. Then D, high seismic vulnerability. And E and F are very high seismic vulnerability and near a major fault. So most areas of high seismic activity are in the western states, including Alaska and Hawaii, and California as well. So the urban quartz drawings actually show the seismic design categories, and also what also we will discuss, we'll see how we'll explain how those elements use selected drawings from the project structural drawings. So stay tuned. Let's take a look at that. So when we talk about forces created by earthquakes, there are a few things we need to remember. So the amount of damage done by a seismic event depends on several factors, including distance from the earthquake's origin or epicenter, the strength and type of earthquake, site soil conditions, and the type of building construction. So during a seismic event, several types of energy waves are introduced into the structure. These include forces that shake the building back and forth, like moving the dish of jello rapidly left and right, and waves, much like the ocean swells, that lift the building up and then drop it. So like there are different variations of shaking and moving that earthquakes create. So the side-to-side motion can come from any direction and cause the building to sway, particularly on the top floors. And the ground waves can also tilt the building as well, cause the building to lift off the foundation. Either of these forces can cause building floors to separate, the building to overturn, or the supporting walls to rack and fail. And this racking would be actually similar to a freestanding row of books being pushed at the top edge until the row fell. So to resist the damage, the structural drawings might be subjected to seismic activity, specify methods to ensure that the foundation design addresses specific site soil conditions. The foundation will hold together as one structural unit. Then the walls will be securely attached to the foundation, and the walls will resist racking and overturning. The walls and floors of each story will be securely attached to the story above and below, and then the floor and roof will lend anti-racking ability to the structure. So these structural design features allow the structure to absorb the energy of the earthquake and provide a load path for the energy to travel back into the ground while leaving the structure intact. So let's take a look at the soil condition. So the site requires a geotech report performed by the engineer, and this provides information of the soil types, strength, characteristics of the various soils present, landslide potential, and any other geologically related hazards. Structures built on rock typically perform better than those built on soils, particularly loose soils. So during earthquakes, some soils are subject to liquefaction, where the soil acts like a liquid, offering the structure no support. The geotechnical report addresses all these concerns and provides information on preparing the site for the foundation. Report also provides the structural engineer the site and soil information needed to design the foundation. So let's talk a little bit about the way we can read the structural drawings. So the structural drawings, actually here in the textbook, you can find those drawings that are included in the packet. So please refer to them because it's nice to watch the video, but it's more important to actually see that, how that is graphically represented. So foundation, concrete is a durable material and good choice for building foundations, but it does have one drawback. While concrete is very strong in compression, it is weak in tension. And when you look at the profile or elevation of a slab, the forces placed on the slab tend to make it deflect or bend, causing a compression phase and a tension phase. And please, again, refer to the images here. You can see when there is a load on the slab, how that reacts and how that starts to crack on the bottom part of it because there is tension and it cannot resist that. So because steel has high tensile strength, steel rebar is added to the tension side of the slab, usually the bottom, and this adds tension strength to the slab. To add even more strength to the slab, a process called post-tensioning is used in addition to using rebar. Post-tensioning involves the placement of a grid of plastic-coated cables in the concrete forms prior to concrete placement. Both ends of each cable penetrate the form and extend past the edge of the slab after concrete placement. So once the concrete is poured, the concrete is allowed to partially cure. It's usually about 7 days, and or until a specific compressive strength is achieved. So that total depends on the manufacturer's recommendations and the architect's and structural engineer recommendations. One end of the tensioning cable is then anchored, and a hydraulic tensioner is used to stretch the cable inside the slab. The plastic coating allows the cable to stretch inside and now solid concrete. So the cables are tensioned to approximately 33,000 pounds, and specs for the spacing in actually how much the cable will be elongated are usually provided as well, together with the drawings and calculations. So post-tension is similar to pre-stressed concrete beams that are used in highway bridges, and the cables are pulling the sides of the concrete slab together, and the slab gains a much higher resistance to tension stresses. Again, please refer to the images. You will see a lot of different configurations. You will see the typical hold down assembly, and you see how the hold downs are used to anchor the first story walls to the foundation and resist the overturning forces. Hold downs are manufactured in a variety of configurations, and they can attach to a bolt embedded in the concrete or be set directly in the concrete. Usually they bolt to a post or stud in the wall, but also can be nailed to the post or studs. And they're a critical part of the shear wall design. The other anchoring system is a series of foundation anchor bolts embedded in the concrete that bolt the wall bottom plate to the concrete, and that resists both uplift and lateral displacement. So again, please refer to the images here. Let's talk a little bit about walls. So any building in earthquake country needs to be braced to resist shear forces. Shear forces are those that move along walls or floors and distort the structure by racking. So the standard shear resistant method is to apply structural sheathing such as plywood or OSB, nailed to the studs and plates in a prescribed manner. Just because shear walls must resist the forces of an earthquake, the size, placement, and spacing of nails is especially important. In areas where with very little seismic activity, it is not customary for construction drawings to specify nailing schedules, but in high seismic areas, nailing is typically preferred by the structural engineer. So, and also, since shear panels cannot continue across the openings, the narrow wall on one side of the opening is paneled each side and has heavy hold downs tying it to the foundation. So again, please refer to the images. And a critical design consideration is that the shear wall sections stack vertically, upper level shear walls occurring directly above the shear walls below. So that is another important thing as well. And we're moving to the floor and roof. So an uninterrupted expanse of floor or roof sheathing creates a strong horizontal shear resistant diaphragm that not only prevents the building from twisting or racking horizontally, but can also share its shear strength with the walls below. Shear transfer details actually are important as well. And These are particularly necessary when there are reentrant or inside corners or other discontinuous load paths in the wall. So that was it for our Unit 36. The next unit, Unit 37, is the first chapter of Part 4, which is heavy construction, heavy commercial construction, and that will be about the school edition described here in this textbook. So I thank you so much for watching, and I will see you in Unit 37.